model for the tower of modular curves.
Okay, thank you. Thank you. All right, so my talk is on those modular curves. By the tower of modular curves, I mean the curves x of p to the n, right? So the right place to start with this is the Katz-Mazur model for the modular curve x of p to the n. So in their notation, I'll start with the open curve. So here we go. So the Katz-Mazur model. All right, so let's say yn is the open curve, y of gamma of p to the n, and p is a prime, and I'll throw in some tame level structure of the form gamma 1 of capital N. So p here is a prime, and it is relatively prime with the positive integer n. And for rigidity's sake, I'll let n be at least 5. And all right, so over Q, of course, we know this is the thing which classifies triples E, phi, P. And phi will be the p to the n level structure. So in other words, phi goes from z mod p to the n z squared to e of p to the n. I mean, so in the naive sense, where yn is really over Q, this gets to be an isomorphism. And this capital P is supposed to be a point of order n. So that's not the Katz-Mazur model. This is over Q. The Katz-Mazur model, I will also write it yn, but let's base extend to, well, OK, we're going to throw in p to the nth roots of unity. But their model lives over something integral, namely zp. And as I said, I'm going to add in zeta p to the nth roots of unity, so that the thing becomes disconnected. And I can describe each connected component of the special fiber. So this thing lives over the integers, and I can draw out this familiar picture of what's happening. So each connected component of yn tensor fp bar is, all right, well, it looks like this kind of configuration where you have Agusa curves which meet simultaneously above the supersingular locus. So here's my picture of one connected component of yn tensor fp bar, and this maps down to y0 tensor fp bar. All right, so remember, y0 has no p to the n level structure at all. It's just y1 of n. And so y0 tensor fp bar, well, that's smooth. It's a smooth curve, smooth open curve. And this map, it's only not smooth. It's only the only singular points occur at the supersingular locus. So to be careful. I mean, all over my notes, it's just SS, but SS could stand for semi-stable and also supersingular, so I just have to be careful. So this is, all right, so they cross over these points. You can sort of see that. I mean, in the case where E is elliptic curve over a finite field, say, I mean, this phi has to have a kernel, and that gives you, that kernel lives in here, and that gives you a kind of discrete invariant. The invariant is a line inside of z mod p to the nz, and that's where each of these components comes in. So each of these components, by the way, is an Agusa curve. All right, they're all practically the same. Yeah, and we have this nice picture. What we're going to do today is, the idea is, in most basic terms, take the model over this ring of integers, possibly extend the base, and then blow up in neighborhoods of these supersingular points, and then describe what the model of the result looks like. OK, so that's our goal for today. Any questions so far? Great. OK. All right, so I can proceed with defining what semistable models are. Right. All right, so let's say k over qp is finite. And OK will be the ring of integers, and p will be the maximal ideal, and k will be the quotient field. All right. And let's say capital X over k is a smooth proper curve. A semi-stable model so the distinction has to be between Roman x and script x. So that's my script x. X over over the ring of integers is, well, it's going to be a proper scheme over spec OK OK with, well, for one thing, it has to actually be a model. So when I tensor with K, the result is just the thing that I started with, right? And then the special fiber, so when I tensor with little k bar, well, this is some scheme in characteristic P, and I want it to have, its only singularities are supposed to be ordinary double crossings. So has only normal crossings as singularities. And normal crossings means that, well, if you take the local ring at that point, at the singular point, and complete it, locally the ring is going to be k bar double brackets xy, modulo xy. So the completed local ring at a singular point has to look like this, just a pair of axes meeting. Okay, so this thing doesn't necessarily exist over K, but if it does, you know, you can kind of think of the X as more of a combinatorial object. So if X is a semi-stable model, maybe X tensor K bar is something like this. So it's got these components. Maybe I'll call them A, B, C, D, and then E. So who knows what these components are, but I want to attach a graph to this, dual graph. It's rather what you would expect. So the vertices now are the irreducible components appearing in the special fiber. And since A and B intersect here, I connect A and B with an edge. So it's this combinatorial object, and this is probably in the way, but that's all right. Well, OK. I won't draw over here. So A, B, right. So A, B, C, OK. C, and then C connects to A. And there's also a D. Oh, no, I see there's a D involved. OK. Great. OK. All right, so now we can just draw this graph, and each of the vertices are labeled with a smooth non-singular curve over K bar, because that's what each of these components are. All right. So, well, what about the existence theorems for these things? Yeah, I probably should just not write over there. I think that's a good idea. So these words. All right. Well, one familiar theorem is that semi-stable models do eventually exist, but you may have to pass to a ramified extension of the base. So this is the Deligne-Mumford theorem. Right, so there exists L over K finite such that XL admits a semi-stable model. All right, so that's more or less familiar. Here's another theorem that kind of by Robert Coleman that relativizes the whole situation and is going to be rather important for us. If X maps to Y is a finite map of smooth proper curves over capital K, there exists L over K and a finite morphism from script X. No, I did this wrong. What I was supposed to do is draw a very Roman Y here. And here we go. Finite morphism from script X to script Y of semi-stable models, which extends XL to YL. So script X and script Y are to be semi-stable models for XL and YL. Okay. So the thing can be done in this relative fashion. I mean, if you just choose a semi-stable model for Y here, there may not exist such a map here that's finite. You may have to do some more blowings up to this model to get this to work out, depending on what the x is. What? Oh, sure, they both have to be blown up. But if you just start with an x and a y, there's no a priori reason why you would have such a morphism which extends the morphism x to y over here.
Oh, but you made it to blow y also.
Yes, you made it to certainly. Yeah, in fact, here's an extreme situation. You may have y just being the projective line. And then depending on what x is, you may have to blow up the projective line anyway just to produce more components. You could sort of see that already. I mean, if x is some complicated thing whose semi-stable model looks like that, a finite map from that to something else, you expect it to have many components. They'll all have to be rational, but you'll have to blow up this thing maybe extra amount of times, even if it is just the projective line. In fact, that's precisely the situation that I would like to prepare you for. Okay. All right, so what I'd like to do is motivate why I care about this problem at all. I mean, modular curves are kind of interesting structures, and maybe you just care about finding nice integral models for them. But another reason is really cohomological. So if interested in, well, maybe H1 is the only interesting cohomology because it's a curve, but oh yeah, k bar. So let's say L is a prime different from the residue characteristic of K, which was P. Well, the thing is, so this is a very opaque object. If X has a nice model, though, if X has a semi-stable model, you can peer into this cohomology. And so I'll just spell out how this plays out. So there exists an exact sequence where the interesting thing is in the middle. Oh, sorry. So if X is semi-stable model for X, there exists an exact sequence where the interesting thing is in the middle, and it's flanked by combinatorial things, which are rather easy. So 0, and then here is H1 of the special fiber. 0. So, all right. So what's going on here? Oh, did I screw up? What? Oh yeah. Thank you. What else could that mean? Yeah. Everything else OK, though? All right, this gamma is the dual graph. So whatever loops are present in gamma contribute cycles to this thing. So this is an exact sequence of what? Of QL bar GK modules. So I mean, if we're interested in this thing as a GK module, this is the story. So the thing on the right is definitely combinatorial. The thing on the left is rather combinatorial also. What do I mean by that? So I mean that the graph gamma, coming along with the structure that it has, I mean its vertices are marked with smooth projective curves over k bar, lowercase k bar. That's all you need to compute what this H1 is. So the cohomology of this, at least up to semi-simplification, is actually quite transparent once you have a semi-stable model. All right. So you can see where I'm going with this, which is that if X is this tower of modular curves, why would I be interested in H1 of it? Well, that encodes modular forms, and there's a lot of arithmetic theory there. OK. All right. So what has been done so far on this sort of problem? Actually, you know what? I think this board will work just fine for this. All right. So what models are known so far for modular curves? I have to remember I end at 3:15. OK. So for the particular case of modular curves, all right, so the most familiar thing possible is just the Deligne-Rappaport model for a curve like x naught of p. It says the special fiber looks like two DNA strands meeting, right? And so here the singularities are really just normal crossings. This is the strand that contains the cusp at infinity. This is the strand that contains the cusp at 0. So as long as the level is very harmless, the thing is visibly semi-stable. If you move up to p squared, and then Adjacency has this result. So Adjacency from 1990, where he computes the special fiber of a stable model for x0 of p squared n. And then kind of the next bit of progress came 20 years later, x0 of p cubed n. And this is the paper of Coleman, McMurdy. And this was just published this year, and it was about 90 pages. But this really has new methods, though, in that the entire thing is rigid analytic. And in fact, that's how I worked, rigid analytically. In fact, we have a semi-stable model for the entire tower, not just x0 of p to the n, but rather x of p to the n, together with all of the appropriate group actions. Okay. All right. All right, so the next thing I have to say is that the only thing that matters, I mean, this talk isn't really about modular curves at all. It's really only about these neighborhoods of the super singular points. And you can rephrase the whole problem in terms of deformations of formal groups and Lubin-Tate theory. And that's really what I have to do here, because the whole pursuit really is local in the neighborhood of a super singular point. So I'll say it this way. You'd only focus on what you might call supersingular regions. So that is, let's choose a supersingular point. I'll call it AQ. And this lives in, well, it lives in Y1 of n. FP bar, and it'll be the supersingular locus. So A is a supersingular elliptic curve. And I'm going to define a subspace Mn inside of Yn. So remember, Yn was the modular curve with p to the n level structure. I mean, maybe I'll just write it. Well, I have gamma of p to the n, rather than assume you've memorized that notation already. So Mn inside of this, well, it's going to be a subspace consisting of those triples E, and then the phi, and then the p. And what I want is that E is a deformation of A. That is, E modulo P is isomorphic to A. And the tame level structures match up too. So P maps to Q, like so. So this Mn is basically moduli for lifts of the A together with a p to the n level structure. And so this thing, all right, so this has this, by the Sayre-Tate theorem, this has this interpretation in terms of deformations of formal modules. And in fact, that observation allows us to basically forget about A, forget about Q, in fact, forget about N. The thing only depends, well, it's just it only depends on lowercase n. That's it. So I'll say it this way. Mn is a Lubin-Tate curve of level p to the n that parametrizes deformations of formal groups. Okay. And what kind of thing is it? Well, it's not a scheme. It's basically just a rigid analytic variety. So Yn here, I should really say that it's not a subset of the scheme Yn. I mean, it's a subset of it's a subspace of the analytification, which you might call Yn rig. So Mn is a rigid analytic curve. Okay. But that's fine. I mean, we can now shift the problem from finding a semi-stable model for xn to finding a semi-stable model for this Mn. So because that's sort of the only problematic area that the modular curve has. Okay. All right, so some interesting things about this Mn. Okay, so it's highly symmetric. And you can see the symmetry when you pass to the inverse limit along the whole tower. So let's say M is this inverse limit. So you see, I mean, Mn maps to Mn minus 1 via degeneracy map. And let's say M is this inverse limit of rigid analytic spaces. And then this M, M, once you base extend to QP bar, emits action by, well, product of 3 groups. So this is the sort of thing that you encounter in non-abelian Lubin Tate theory. One of the groups comes from the phi, the level structure. It's a GL2 group, so it's GL2 QP. Okay. Another one is, well, it's going to be a quaternionic group, so B cross. So where does that come from? So let's say OB is the endomorphism algebra of A. Well, it's tensor with ZP. So A was super singular, right? So this is going to be an order inside of a quaternion algebra over QP. So B will just be OB tensor QP. I guess I could have just said end A tensor QP for B, but all right. And so this is a quaternion. This is a ramified quaternion algebra over QP. It's basically the only one. And then finally, it has an action of the Weil group, WQP. Okay. So I'm not going to define how each of these actions work. I'm just going to be very impressionistic. But you can see a GL2ZP at least acting by means of this, the level structure. And then the B comes from the endomorphisms of the thing that you're deforming. And then the Weil group comes because you've base extended to the algebraic closure over here. Okay. So far, so good? It's a Weil group. The thing is, M isn't defined, well, yeah. Unfortunately, M isn't defined over QP, just QP. I mean, you could see that if maybe the thing is A is not defined over FP. Maybe you have to pass to some extension of FP even to see A. And that indicates that M isn't really defined over QP at all. It's basically defined over QP unramified. So the action of inertia on this thing is clear. And then the action of a Frobenius is actually a very subtle issue. It's not at all obvious that how the Frobenius can act. But yes, it's only the Weil group. It's not the whole Galois group. Yeah. And actually, I'm lying about the fact that this whole triple product group even acts. It's actually a subgroup by, and I'll see, if you don't want to write down this parenthesis, you don't have to. So a subgroup of this, and then the parenthesis continues, of index Z. So imagine a map from this triple product group to Z given by valuation of determinant times valuation of norm times valuation here. And the kernel is what really does the acting here. Okay. All right, so then the theorem that I want to say next has to do with what the cohomology of M is. It turns out it realizes the correspondences between representations of these groups. Okay. Then, well, I'll say theorem, and this I'll attribute it to Deligne, but the paper is written by Carriol. So theorem of Deligne-Carriol, which is that the cohomology of this guy, so H1 with compact supports of the M with coefficients in QL bar, well, it's isomorphic to the following direct sum over all discrete series representations pi of GL2 QP with coefficients in QL bar, of course, of now it's pi tensor JL of pi tensor sigma of pi. And so this JL of pi is the Jacquet Langlands correspondence, and this sigma of pi as well, it's some normalization of the local Langlands correspondence. So Langlands correspondence. Okay, and so the generalization of this to higher dimensional deformation spaces is exactly what was done in the work of Harris and Taylor, just for GLN. Here, well, okay, there is some more parenthetical thing to act because it's only a subgroup acting. So you have to say, well, it's the sum of pi's up to unramified twists, and then it's really this product restricted to whatever subgroup really does do the acting. But you can adjust the statement so that it actually is correct. Okay. All right, so okay, so now we have all of these semi-stable models for curves at various levels, but I really think that the right way to do this project, to find the semi-stable model for a particular curve, it must interface with this picture, this cohomological picture. All right, so this is actually what happens, and in fact it interfaces not only with just this theorem, but with this whole theory of Bushnell-Kutzko types. Well, supercuspidal, but you also get the Steinberg representations as well, because they appear at the boundary of the Lubin-Tate space. Anything else?
You don't get all the,
Oh God, yeah. Okay, yeah, you're right. I think if what I understand your complaint is, it's absolutely correct. This sigma fails to be the local Langlands correspondence when pi is the Steinberg representation. So Jean-Francois can tell you lots about that, right? But if pi is it fails to be supercuspidal, this sigma of pi is not two-dimensional. It's just one-dimensional. Is that what you were asking?
I was not asking. He was asking.
Oh, why did I? Oh, sorry, I didn't know it was coming. I am sorry about that. Yeah. Okay, pardon me. All right, so moving on. So what was the technique for doing this? So I really borrowed the technique of Coleman and McMurdy for finding the semi-stable reduction of x naught of p cubed, which is this method of semi-stable coverings. So this is think of semi-stable coverings. All right, so the goal is to find a semi-stable model for these MNs. The MNs are rigid analytic spaces. I didn't quite define what it means to have a semi-stable model for that. It's a formal scheme whose special fiber has the right properties. But it turns out that giving one of those, finding the right model for MN, is equivalent to giving a semi-stable covering. Now, what is that? All right, so the whole theory is due to Coleman. Okay, so a sketch of it is that you express whatever space you're working with, X, as a union of spaces Wi. So this is going to be an open covering. The Wi's are Coleman's wide opens. Okay, so in rigid analytic geometry, it really isn't enough to say something is open. You have to say what kind of open it is. So wide open means the following thing. It means conformal to a C minus a D. And the C is something proper over K, let's say whatever your non-Archimedean field is. And D is a disjoint union of disks. So this is the kind of species of open set that we use in our covering. It's something proper, but you've just excised closed disks out of it. And what's left over is something open, and that's what Coleman calls wide opens. Okay.
I want to understand a little better this. In what sense you have a rigid analytic space? So the bonds, if I think first to the measure Katz-Mazur,
Yes?
is everything falling to the supersingularities?
Oh, yes.
Finite union, or would you have something infinite?
Yeah, very good question. So these objects, these MNs, these rigid analytic curves, are by no means anything proper. They're open. By the way, M0 is an open disk. And so any covering that you give is is going to have to be infinite. So these coverings are actually going to be infinite. The graphs we construct will be infinite graphs.
At the end, it will be something very simple.
At the end, what do you mean?
At the boundary.
Oh, the boundary. So yeah, you're getting it. So the graphs that we draw will be infinite. They will have ends, by which I mean rays that go off to infinity. Each such end corresponds to the boundary. Okay, good. All right. So so in Coleman's setup, by the way, X started up as something proper, but we don't have to consider it like that. Our X could be this Mn over here. Okay. So Wi is a wide open curve. Oh, okay. Such that, and then kind of this axiomatic list of properties. So two of these guys have to intersect nicely. And in fact, Wi intersect Wj has to be a disjoint union of annuli, a rigid analytic open annuli. An annulus kind of corresponds to an intersection of two components of the special fiber. No three are allowed to intersect. So so if I, j, k are different indices, they're not allowed to intersect by threes. And then finally, oh, I've run out of room. Well, yeah, OK. Finally, I have to say something about something having good reduction, something having non-singular reduction. And that's the idea that if you take one of these wide opens and you remove all those open annuli that arise from intersections, so if zi is wi minus everything you get from all the other wj. No, it should be this way. J not equal to I. I like that better. So wi, and then remove everything coming from other wide opens. This inside of wi is closed. It's an aphanoid. You've kind of stripped it of its boundary annuli, its sleeves. And what's left over is an aphanoid. And I demand that zi bar is non-singular. All right, so these three axioms, so the intersections have to work properly. And then each wi has something non-singular at its core. Having one of these is one and the same as having a semi-stable model for your object x, for your rigid curve x. So these data, and this is still just Coleman's work, give a model x of x with semi-stable reduction. Oh, well, yes. So any particular mn, I imagine you won't have to go to some infinite extension. But for the whole tower, yes. I'm not even talking about the whole tower yet. I'm just talking about one in particular. Okay. So they give a model. So it's a formal scheme whose generic fiber is the x. And the semi-stable reduction. And what does the reduction look like? Well, yeah, OK. So x bar, I'll write it. And it's going to be a union over the i's of, well, it's sort of what you expect. So we have a non-singular curve mod p to work with here. But I have to take the projective closure of it. So I'll write CL for the unique projective model of that thing. I mean, this zi bar is going to be an affine, whereas really we want to sew together projective things. So it's the union of these modulos, the obvious gluing data. You see, when wi intersects wj, that corresponds to a point at infinity of zi meeting a point at infinity of zj. Okay. So this is a whole rigid analytic framework that we can do this whole project in. Yes?
Yeah, and then analog to higher dimension?
What a good question. Is there an analog of this for higher dimension? I don't know. Certainly you have the geometric notion of generalized semi-stable scheme. So you could have a generalized semi-stable model for a variety of higher dimension. But I don't know if these axioms, I mean, the most naive thing would be to define polyannuli and demand these things. But I just don't know if the theory works out. One big concern I have is that there is no longer a unique projective, there's no longer this operation closure. And I think that's a big problem. I think if z bar is something complicated and affine with no obvious projective model, I don't think you can do this. So I think there is some generalization, but I think it hasn't been discovered yet. Yeah. Obviously, that's going to be very important. Okay. All right. I have 20 minutes. Mm-hmm. Oh, yeah. Yeah, that's right. That's right. So, oh, yeah, I should actually say something like that. So, yeah, but I'll say it over here. So it's a short statement. So if you happen to have that semi-stable model, then you can deduce results on the cohomology of x. But I already said something like that, didn't I? Yeah, you have that exact sequence. Yeah. But that exact sequence. Yeah, so there's going to be a relationship between h1 of x compactly supported and the direct sum over all I of h1 of zi. It's L-adic coefficients. So there's going to be a relationship between these two objects, and I don't want to say that it's an isomorphism, but somehow it sits in an exact sequence like this, where this part comes from the boundary. So there is something like this that happens.
I think they could use this Treff covering to compute cohomology.
Yeah, directly. Yeah, via Meyer-via-Torres sequence or something like that. Yeah, absolutely. So, but you still have to worry about boundary terms. So I was saying there's going to be some exact sequence like this. The kernel comes from the boundary somehow. Yeah. All right. So now we're going to talk about results. Ooh. Okay. All right, so I'll just remind everyone of notation. So we had yn was our modular curve. And this mn inside of yn was a supersingular region. And I indicated, although I didn't write it down, that finding a semi-stable model for the mn is for all of the mn's is tantamount for finding a semi-stable model for yn, because all of the trouble comes from the supersingular regions. Okay, so the results are as follows. So we found semi-stable models. So I'll write script mn over, okay, you have to pass to something like zp bar. Ring of integers is in an algebraic closure. For mn, such that, okay, so the following properties. Oh, yeah, right, so I've already said a lie. So actually, it's not over mn. For my purposes, and this is going to be completely bizarre, but you have to take mn and remove its CM points. You see, some of these deformations of formal groups have extra endomorphisms, and those are the areas that are the most singular. And you have to get rid of them in order to do this. There's some they form like a discrete subgroup of this, subset of this, so this is not so problematic. Okay, but such that, so more on that later. Oh, okay. Such that, so first of all, the transition maps are finite. Is finite. So by Coleman's result, this sort of thing can always be done for a particular pair, for a particular morphism. And I'm saying it can be done for the whole tower, all the way up. Another thing is that the model mn, so remember this capital M has this action by all these groups, but I'm saying that this mn is GL2QP. So it's equivariant by the action of the appropriate groups. Equivariant. This is shorthand for saying that the whole tower is equivariant. I mean that whatever subgroup really does act on mn, it's equivariant for that. Yeah. All right, so those are. So I feel like those properties are things that could be established formally, like the existence of such models, like that could be established formally. But this next property is a complete miracle. So this is the thing that you would really not expect to happen unless you were in some special situation. So mn, all right, so the tower has the following property. And I haven't settled on a name for this property, but for the moment I'm provisionally calling it stably inseparable. I don't like that phrase at all, so if you can suggest a better one. So let me say what the property is. So let's take our mn and reduce it mod p. And I get this tower of curves over fp. Each one is this configuration of components. They're all non-singular. What did I say? FP bar, yeah. So each one is a scheme over FP bar. Each one is a configuration of components. It's not a finite type, but it's locally a finite type over FP bar. And now let's pick, inside of MN, let's pick a connected component. No, let's pick a irreducible component. And so these are all irreducible. No, yeah, they're all irreducible components. That is, choose a connected component here, lift it to a connected component here. All of these maps are finite. So once you've picked something here, you can always find a connected component here that in its inverse image and so forth up the tower. Now, I haven't said anything. I haven't imposed any condition yet. But in this tower, what you can imagine happening is that the genus of this, it gets larger here and so forth, and the genera just go up to infinity. For instance, the tower of Augusta curves on the ordinary locus does exactly that. There are all these non-singular curves, and the genera goes up to infinity. But that doesn't happen here. These transition maps all become inseparable for n large enough. So that's the story. Then we'll just continue that statement over here. Then Mn maps to Mn minus 1. No. Cn maps to Cn minus 1 is purely inseparable for n large enough. Which means if you have a purely inseparable map between non-singular projective curves and characteristic P, the genera are equal. The map becomes an isomorphism on the level of L-adic cohomology. So, so the genera just stay stable. So I'm calling it stably inseparable. I don't know. Okay. And so what we can do is, no component could ever map to a point because these are all finite. These are all the maps on the transition maps between models are finite, and so they're finite. These maps are also finite. So you can't have any component here contracting to a point. That's why it's always possible to start with any component here and then. Oh yeah, okay. It's also okay. All right, so this is the way that it works. And now, given that this is the way that it works, what I'm going to do is attach something combinatorial to this whole picture.
Can you repeat what you mean by equivalent for this big group?
Right. Yeah. Okay. But it's in.
For example, if you take some G, so element G into GL2 of P.
Yeah. Okay.
It will change the.
Right. Right.
So do you have a canonical model for this?
Yes. So I mean, you're right. I mean, if I have some particular element of GL2QP, it may not stabilize the Mn. It may move the Mn to some other Mn.
But you have some canonical morphism between your Mn and some.
Yes. So that's a non-trivial thing that I'm kind of claiming is going to happen. It moves.
This is what you mean by equivalent.
Yes. Yes. Exactly. Yes. All right. So I mean I need that condition because what I'm going to write down next, this combinatorial object, must also have an action by that group. All right, so let's say gamma, let gamma be the dual graph arising from all this data. So what is that supposed to mean? A vertex of this gamma is supposed to be a connected component, like it was over there on that board. By a connected component, I mean one of these chains. So vertices are these chains of irreducible components. So our chains Ci to Ci minus 1 and so forth. And what's the adjacency condition? Well, it's the only one it could possibly be. If you line up two of these chains and if the corresponding irreducible components are adjacent in each one, then you say that these two vertices are going to be adjacent in the dual graph. So so we have this graph here, and then you can label each vertex V and gamma with one of these components Cn, where n is large enough so that the transition maps are going to be purely inseparable. So it's going to be like an enhanced graph. It's labeled with these CNs. I don't like that it depends on n, though. But really, the right thing to do is to work in a different category. The category of schemes over FP bar where inseparable maps have been inverted. And then you can label the vertex with something that only depends on the vertex. Okay. But if you like, label it with Cn where n is large enough. Okay. All right, is that all clear so far?
So the set of vertices is at least locally something profinite?
Yeah, I mean, it's just locally finite. I mean, it's just the graph of it is.
If you don't, this projective limit, you don't have that starting from a component, you have 2 above 4 and more components.
Oh, as far as connected components go, you're right. There are uncountably many connected components. So the space of connected components is profinite and uncountably infinite. But each connected component of the gamma is just, it's locally finite. I mean, it's a connected thing. Yeah. I mean, each vertex only has finitely many neighbors and so forth. It's not profinite. I mean, each connected component is not profinite. That's true. Yeah.
So if you take this tau over FP,
Yeah.
if you take one irreducible component, above it you
Yeah.
will have infinitely many or a finite?
No, only finitely many. Because these transition maps are finite.
Yes, but
So.
it could multiply the number of irreducible components.
But when you go upstairs.
Oh, yeah, I mean, there's infinitely many components that pass through the one that you've chosen, yes.
That maps to it.
That maps to it. Yes. I mean, if you take gamma and you mod out by one of these compact opens, you'll get the dual graph. Perhaps Kn is like a p-adic version of gamma of Pn. And this is the dual graph for Mn. That's true. But now, what is your question? I mean, this dual graph.
If I take the projective limit,
Oh, yes. But the thing is, it was confusing because you said, is the thing profinite? And it's not, because this graph is not finite.
oh yes.
Because as we said, these things are open, these curves are open, and you need infinitely many components to cover them. Right. OK. All right. So and then how does this whole picture interface with non-abelian Lubin-Tate theory, with the theorem of Deligne-Cariol? Well, all right. I don't need this statement, but then well, I'll just write the following kind of isomorphism. So this sum over pi is of pi tensor JL of pi tensor sigma of pi. And now I just want the supercuspidal ones. So this appears inside of the cohomology of our tau or m. But I'll just write this, the supercuspidal part. It's a quotient of this thing. But on the other hand, because now we have this semi-stable covering, we can say that this is a sum, direct sum over all the vertices v that appear in the graph of h1 of the Cn. So I'll write that as Cv. So Cv is going to be a curve that appears in this chain over here, in one of these chains. So to each vertex, you can associate a curve, a projective curve over Fp bar up to inseparable morphism. But then when you take h1 of it, it doesn't matter which of the ends you pick. So this thing is well defined, even if this is not so well defined. Okay. All right. And now I can even make this, if you like. I mean, I can take this and arrange it into orbits. I mean, I can take the sum over v inside of gamma modulo GL2F cross B star. I'm just going to take this sum and rearrange it and just separate it into orbits under the action of this group. And what we'll get is the induced representation. What?
What's F?
There is no F. Oh, F. Oh, F. Oh, F. Thank you. Thank you. Thank you. F is QP. There is no F. Right. See, I'm used to writing F because this result works in more generality than QP. F could be another local field. Okay. Gamma mod GL2 QP cross B cross. Okay. Of an induced representation. So for each vertex, I'm going to let KV subset GL2 QP cross B cross be the stabilizer of V. And now I'm arranging things into orbits. So the orbit corresponding to the V, I mean, representation theoretically, it's the induced module from KV up to the whole thing, QP cross B cross, of H1 of CV. Yeah, with QL bar coefficients. Okay. So now in this equation, we've got on the left side a sum over all the supercuspidals, and on the right side, a sum of these induced representations from these open and compact mod center subgroups. It turns out that's how they are. And this recalls this whole theory of types of Bushnell-Kutzko. So I'm not going to say all the details of this, but it interfaces very, very nicely. So every supercuspidal is induced from a from an open compact mod center subgroup, and that theory can be read off by what's going on here. So in lieu of doing that, of explaining that, I'll just show you a picture of the graph gamma, which is maybe the right way to present this. So here we go. Okay. So I need the screen to come down. Yeah. So while this is happening, are there any questions? Yeah, do I have any control over the fields? Yes, the fields can be described explicitly once you know the local Langlands correspondence well enough. So a particular pi yields a sigma of pi, and that's you take the kernel of that Gala representation, and that's the field you need to pass to. I mean, the short answer is yes, it can be done. All right, so okay, so let me just. Yeah, M0 is a semi-stable model for the open ball, but it's rather complicated. It's already sort of complicated. Full screen mode. Okay. Okay, good. All right. So what I'm doing to describe for you now is that graph gamma. The gamma has an action of a GL2 group, a quaternion algebra, and the Galois group, and here is just part of the graph. So I'm calling it the tame part of the graph. And it corresponds, well, we'll see what it says later. But first, the structure of it is it's this Bruhat-Titz tree for GL2 of QP. So the case of P equals 3 is displayed here. So each blue vertex has degree 4, P plus 1 generally. And the blue vertices represent that curve, xy to the P minus x to the Py equals 1. That curve is the Deligne-Lustig variety for SL2 FP. The black vertices are just P1. Okay. All right, is that good enough? All right, oh yes, I have some more, more info on that. So GL2 QP acts on this whole picture. The stabilizer of any particular vertex, like the center one, say, is SL2 ZP. And then I have to tell you how SL2 ZP acts on the curve that corresponds to that point. Yes?
It's equal to the curve, you mean like the inseparable class of
Yeah. Yeah, Florian makes this point that really the markings of each vertex are just like inseparable, I don't know how to call it, classes of curves, of projective smooth curves over FP bar up to purely inseparable morphism.
You can just take the inseparable closure of the field of Axel if you want.
Yeah. Your point is that the real invariant thing here is the field you get when you take the inseparable closure of the function field of x. Yeah, that's a really good point. Yeah. Okay, I have to tell you how now SL2 ZP acts on the curve x over here.
This graph is for
It's for x0 of p squared.
P squared.
Yeah, yeah, okay. I have to tell you how SL2ZP acts on the curve x. It acts by that formula. Okay. But you check that this, this action preserves that equation. It does. And then the H1 of this is going to be this representation of GL2QP. It decomposes as a direct sum of the supercuspidal representations of conductor P squared. And that's kind of the tame case. Okay. And the Galois representations coming from such supercuspidal pi are exactly the tamely ramified, irreducible representations of GQP. Oh, that's a really good question. So there's this corresponding other object, the Drinfeld upper half plane. And coverings of it ought to have similar properties in that they realize all the correspondences as well. So I haven't worked out all the details, but I think there has to be a relationship between this picture and that picture. I mean, the same groups interact.
Can you explain if you go from 1n to n plus 1? So here it's a picture for p squared, but how do you go from p squared to p to...
Oh, yeah, so, well, only p squared is sort of the lowest you see, because p is already, it can't be a conductor of a supercuspidal representation. So this is sort of the bottom.
It will mean you have some Raffanel curve and some tree of Raffanel curve or something like that.
Tree of what?
Of Raffanel curve.
Rational curves.
No?
Well, the curves are not rational because
No,
they
not
have to
here,
be.
but for x, for p, for x0, for x of p or...
Oh, for x of p.
Yes.
Yeah, for x of p, to see what happens with x of p. Yeah, that's a good, okay, yeah, I can explain. You have to take this picture and mod out by gamma of p.
Yes.
And that kills all of the blue vertices except for one. So by kill, I mean it turns into a rational component. But it doesn't kill the center vertex. The center vertex, being fixed by gamma of p, remains blue. So you get this picture where you've got one. It's so, this really should be a bigger thing. The center one, the guys of degree 4 are supposed to be blue, and the guys of degree 2 are supposed to be black. So maybe when I do this next, I'll do different colors or bigger things or anything. But the model of x of p that you get includes one blue vertex. The rest are black. You just get some projective curves. Okay. Now, take this whole thing.
So because
Oh.
on x0 on x of p, you already see something supercuspidal, but
On x of p, you see something
supercuspidal.
supercuspidal.
Yes, which
Yeah.
is
Yeah.
in this blue, but
Yes, that's right. That's right. Yeah, exactly. Okay. All right, take that picture and put it on the floor. That's just level 0 of a whole picture that we're going to add on this. Okay. All right. So there are other components whose Galois representations are wild, and they sprout out of these other vertices. So okay. So out of the blue vertices come green vertices. Out of the black vertices come red vertices. So what's going on here? So I need to introduce the legend. So I only saw 4 isomorphism classes of curves. So out of the blue vertices come they're all Artin Schreier. So all these greens and reds are all these Artin Schreier covers of the affine line. And I've done something else. I've kind of labeled. Oh, it's over. Well, maybe I'll explain this part last time. But there's some connection to the Galois representations that have to appear in the cohomology of this picture. Okay. And so, and one of these trees sprouts out of all of these vertices. So I don't know, to put it all on the same page, it gets a picture like this. So there's like the tree is in the middle, and then all of these things come out. And GL2QP and the quaternion algebra and the Galois group, they all act on this picture.
can you tell how you map one level to the previous one?
So
all those green things map to the blue one?
no, there's no maps between these curves. All you get, I mean, this is kind of what's going on at infinite level already. To see the semi-stable model for a particular x of p to the n, you have to take this picture and mod it by gamma of p to the n. And doing that results in something very complicated. What it's going to do is turn all but finitely many of the components into rational components, and those that survive contribute to the cohomology classes. But even for x of p squared, the picture that you get is so complicated, I don't think it's worth writing down. Thank you.